everyone. Thank you for joining us in this session. We're going to spend the next hour together learning a lot about how Netflix does capacity modeling. My name is Prateek Sharma. I'm a solutions architect with AWS. And I have the pleasure to introduce Joey Lynch today. Joey is a principal software engineer working at Netflix with the data platform teams. He's also very active in the open source community and has contributed to many popular open source projects, such as Apache Cassandra. He's a phenomenal technologist and genuinely very nice guy to work with. So I'm really glad you're all going to meet him today. So AWS has many EC2 families and instance types. And Joey and his team has created a fantastic system to model how to choose EC2 resources that are most optimal for any given workload, ranging from a database system to a stateless Java application. I think this is a really cool system that his team has developed, and I think you're going to have a lovely time learning more about it. So, Joey, please welcome Joey Lynch.
Thank you so much, Prateek, for that wonderful, warm welcome. So today, we're going to be walking through a bit of how Netflix capacity plans optimally in the cloud. And we'll be covering a multitude of workloads, and we'll be diving into some math, but I promise it's good math. It's not hard math, it's good math. And at the end of the day, we will have an understanding of EC2 hardware, how do we characterize it, how do we plan workloads, and then how do we monitor that we're making the right choices? Because today we'll be talking a lot about models, and the one thing that I know about models is that models are rarely true, but they sometimes are useful. And so we're going to be talking about a number of useful models today, but we are going to close this talk with how do you monitor that you made the right choices, because the reality is that sometimes you didn't. And before I dive into the talk, I do want to do the open source plug. The entire system that we'll be talking about today is open source. It's on Netflix Skunkworks GitHub, and throughout the talk I'll be sprinkling in little links to the relevant code that's explaining, if you really want to dive into the code, you can do that either here or later. All right, so this talk is going to be revolving around this equation. We have some workload capacity model, and this workload might be something as simple as a stateless Java app or something as complicated as a Cassandra database handling millions of requests per second. We have an input to this workload capacity model of what the user wants. So they're going to give us some description of, like, I want this kind of database with this kind of capacity. And then we will compose that with a hardware profile, which is how we describe hardware, and your company's current pricing and lifecycle for that hardware. As we'll see in a second, this information is quite dynamic, and it depends a lot on who's using the system. And then ideally, our workload capacity model can output a candidate cluster of a concrete set of computers that you're going to buy to optimally serve that workload. All right, so let's get started, and let's understand computers. And this is the first part of using computers to buy computers. It's really exciting. I'm very excited. All right, and this will fill in the two parts of the equation, the hardware profile and the pricing and lifecycle. All right, so who's familiar with this page? Who's gone to this? Yeah, I hope everybody. Come on, we're at AWS reInvent. Come on. You go to this page and you see a lot of options, right? Like we're presented with, is my workload compute or is it memory? Is it storage? Which one do I go to? And then once you pick a tab, you're then confronted with, like, okay, well, there are all these different generations and different sizes, different classes, different architectures. And when you click on one of those, you're presented with pages like this where you have 32 different sizes. Like, do you want big computers? Do you want small computers? Let's have empathy. This is hard, right? Like as a human, when you see this, you're like, wow, that's a lot of things for me to go pick. And so you probably just Google, what do people use for this? And then you just go buy those computers. But at Netflix, we thought that was maybe not the best way to purchase hardware. And the first step is, like, well, we can take the information on this page and we can make it concrete, right? Like this statement on the slide of this instance is 15% faster in price performance than M5s. We can actually mathematically model what that actually means, and we can break it down in a way that we can reproducibly pick hardware. But even once we think about just, well, what's the computer we're buying, we also have to ask the question of how much money does that computer cost? Because depending on where in the world we're buying it, And depending on what your company negotiates in terms of reserved instances, whether you buy ahead of time, upfront, partial upfront, these prices change. And they change as your company renegotiates with Amazon. And I just thought this was interesting, that as a human, we are trying to make a choice between 139,000 options. This is amazing, right? That there's a cloud that gives you 139,000 options. But at the same time, it's a little bit scary, right? Like, how are we gonna pick what's right? Well, the way that we're going to do that is we're going to kind of dive in and we're going to break it down. So at first, we're going to answer concretely how much CPU, RAM, network, and disk space are actually on these computers. And then we're going to also look at how fast are those CPUs, NICs, and hard drives. Because the reality is that not all CPUs are created equal, not all hard drives are the same speed, and networks are certainly not all the same. But that's not enough. It's not enough to know the concrete attributes of a computer. We also have to understand your company's current life cycle and price. So life cycle is how Netflix talks about friends don't let friends launch M2s, right? Like nobody should ever do that. That is an instance type that is so old, it's strictly dominated by all other ones. And somebody at Netflix makes this call of this is an instance type that we're just not even going to consider in our search space anymore. And then, of course, there's price. So the good news is that we can measure the first two. We can scientifically measure the first two, and then you can just provide the last two. All right, let's dive in. So here is an example of, in the service capacity modeling library, a description of M5D. So we start with the easy stuff, like how many CPUs are there? What frequency are they running at? How much actual RAM is there in base 2? What kind of network bandwidth will we get? And we'll notice that in order to capacity plan, we can't capacity plan with up to 10 gigabit, right? We need to actually know how much dedicated bandwidth does this instance type have. And then if you keep going, you'll see what I think are some pretty cool stuff, like how fast are the drives on M5Ds. So this information is something that is not published for good reason, right? Like the cloud provider wants to be able to switch the underlying hard drives and not be, pinned into a particular implementation. But for us trying to capacity plan, we need to know how fast these drives are, because that actually matters a lot in important questions, like how much memory to buy. So let's dive into a concrete example of how would we actually do this. Well, we just launch the instances. We gather the basic properties from proc-mem info, proc-CPU info. And then kind of the more interesting part is we use a suite of benchmarking tools like iPerf, NetPerf, FIO. NDBench is a Netflix-specific application-level benchmarking framework. We generate load, and then we can measure the latency distributions of the networks, of the drives, using tools like BCC and BPF trace. So this is a screenshot from one of the helper notebooks in the library. If you go to the library/notebooks, we have an example of how do you actually measure disk latency. Well, you apply a load, and then you use BioSnoop to measure the latency of every single disk I/O that is hitting disk. And you can produce these nice distributions. So this is actually real data from a number of M5D instances. And the dark green kind of box plot, that's real actual data coming off of EC2 instances. The nice curve is a fit beta distribution, where we've taken the kind of gathered data, and then we've asked what beta distribution kind of best fits this data. And the reason for this is because trying to share that data is really hard, right? We're talking about large amounts of latency information. But sharing the 3-point statistics, it's a beta distribution with an average value of 110 microseconds and a 5th percentile of 80 microseconds and a 95th percentile of 160 microseconds. That's really easy to share. So we can kind of summarize a lot of complex information into a best fit distribution. And we'll see throughout this talk that we actually do this trick a lot, where we take something that's really complex and we try to kind of model it with a beta distribution. But it's not just limited to disks. You can also measure your network. Just start up an iPerf run. The only kind of interesting thing with measuring network is that EC2 has this really useful feature called burst, where your instance can temporarily go above its baseline provisioned network, which is really useful for when you're booting an instance or doing a backup. It's a very useful feature. But it's really problematic when you're trying to buy computers for the long run, because if you make decisions based on that top line, which you'll notice, you get that top line burst network for about 20 minutes on this instance. So if you just start up the test and you measure immediately, you're going to get the wrong value. You have to wait until the burst bucket kind of exhausts, and then you can measure the real value, in this case 2.5 gigabits. So we've seen how to measure kind of disk latency, network latency, CPU latency. But how does Netflix think about hardware lifecycle? we generally think about hardware progressing through this phase. So when we're first starting new hardware, we call it alpha, and the capacity planners don't recommend any alpha hardware. Those are purely for people who are excited to go do experiments, like myself. Then the average developer starts seeing hardware when it hits beta or stable, and that's when a particular instance type is starting to be used in production in NFX. Stable usually means that you're perfectly fine to buy multiple year reservations on that. It works really well. Deprecated end of life is really important though, because those two states are what allow us to cut off probably about 90% of the search space in this problem by essentially reducing those 100,000 plus options down to maybe a couple hundred. We'll see why that's important in a moment. But we go beyond just lifecycle. We also provide a centralized service for lifecycle and pricing of every instance type that you could possibly launch at Netflix. And this is a rough example of that. But the thing that I want to call out is that as a consumer of this API, as a consumer, the service capacity modeling system just needs to know the cost of an instance. So that's the rate. It doesn't need to know whether at that time we've bought reservations, which is the reserved rate, or if we're going on demand, which is the on-demand rate. We just need to know this kind of currently, how much money are we going to pay Amazon to launch this instance? And I just want to call out here that the library has been built from the beginning for you to bring your own lifecycle, for you to bring your own pricing. Because we recognized very early on that this isn't a very useful system if we have to open source Netflix's choices. Those aren't going to be your choices. And in fact, it actually supports any type of hardware. It doesn't have to be an EC2 instance. It could be some other cloud, although I don't know why you'd want to do that. All right, so I think we've now been very precise about what computers are, what they mean, how we're going to be able to use them. But now we need to start dealing with a slightly more complex problem, which is how does your user tell you what they want? Which it sounds like an easy question, but it's actually extremely difficult. Because the user desire is a key component to this equation. We can't answer the cluster if we don't know what they want. And the problem with this is that the user input probably isn't that easy to get. So I call this the Kubernetes model of the problem with picking instance types is that they're instance types. It would be easier if we gave people more choices. Right? If we let them pick exactly 3 CPUs and 7.5 gigs of RAM, that will somehow make this problem easier. The reality is that they probably don't know how much CPU, RAM, network, disk space, or disk I/O they need for a workload. I don't know that, and I'm a distributed systems database engineer. I can't do this either in my head. So then you go, okay, well, if they don't know that, then maybe they know how much traffic they'll send and how big their request will be and what the distribution will be. And then you go, wait, no, they probably don't know that either. And so now you're kind of stuck. You're like, okay, well, they might be able to give me something, right? And what we realized at Netflix was that they actually probably do know order of magnitude estimates. So they don't know exactly how many QPS they'll send. They don't know exactly how much data they'll store. But they probably know if it's a petabyte or a gigabyte. They probably know if it's 10,000 per second or 100,000 per second. And this led us to phrase our user inputs as intervals. And this is just a slide where I wanted to just demonstrate the power of having your user provide their input in intervals instead of values. So instead of them telling you, I'm going to do 10,000 QPS, they can tell you things like, I think it'll be 1,000 QPS, and my 5th percentile is 100, and my 95th percentile is 9,990. And then we can just fit this nice little skew right blue distribution on the screen. And one of the really neat things about beta distributions is that you can approximate almost any common statistical distribution. Who's familiar with normal distributions? Normal distributions, uniforms. Yeah, so beta is the ultimate distribution because you can use it to model almost anything else. The green one is very close to a uniform. You can model direct deltas by having a very narrow interval. You can model gammas by skewing them one direction. And then the purple one is essentially a shift to normal. So beta distributions are quite useful because you can capture a lot of different types of interval inputs and capture a lot of different complex inputs here. And we're going to leverage that a lot in this model. All right, so let's dive in and look at what a capacity desire is. At the top layer, it's 3 inputs. It's what tier is this desire? So how important, how critical is this cluster? How are people going to query it? That's the query pattern. What kind of QPS, what kind of access pattern? And then for stateful services, what kind of data are they going to be computing on? Or the data shape, as we call it. And service tier is a single number that we like to wrap up a large amount of context into. And I like to joke that service tier is how sad are you if this cluster fails? And more concretely, it is a trade-off of how much do I want to over-provision this thing? Like how much money do I want to throw at the problem so that I don't get woken up at 2 in the morning? And when you have a tier 0 cluster, you probably want to throw some money at that. Versus a tier 3, a tier 3 is like a testing, who cares about it workload. A tier 3, you would much rather save the money and risk the outage because it has no cost to your business. And just one thing I want to point out about tiering, which was something that took a little while for us to realize, was that tiering has very little to do with where code is deployed. So historically at Netflix, people would say like production is important and test is unimportant. And it turns out that that's actually false, right? Like you have things like your artifact store or even the databases that run your CI/CD systems in test, and those are very important, right? They're very critical to your organization, even if they're not in the production environment. So we use this one number, and we'll see this come up later when we're trying to figure out like how much over-provisioning should we use. All right, but what about query pattern? Query pattern is where it starts getting interesting because we start enumerating like a bunch of inputs, and you'll probably notice that some of these the user probably doesn't know. So we'll figure out where we get those in a second. So a query pattern is like an access pattern. Is this latency? Is this throughput? What kind of consistency do they expect? Do they expect strong consistency out of this workload? Do they expect eventual consistency? Turns out strong consistency more expensive than eventual consistency. And something that the user probably is going to give us is their estimated reads and writes per second. And one of the things that we evaluated here was whether we should have just a QPS number. Because even asking people to kind of split their workload into these 2 query categories actually was kind of hard for some people. And we kind of evaluated like, well, on the one end, we could have just one, like, what's your QPS? On the other end, we could have like very sophisticated, like tell us every possible query pattern that you could have and what's your QPS for each one of those. And what we settled on was a compromise where we said, well, just giving people 2 choices between read and mutative operations, that seems to be a good compromise in what people can realistically give us. And then finally, a very important input is how expensive are those reads and writes. So for example, a SQL database, a read is arbitrarily expensive. Versus a Memcache data store, a read is rather limited in how much on CPU time it can cost. So the mean read latency and mean write latency on CPU time are something that's very important for capacity planning. But the human probably doesn't know that, right? Like the person who's asking you to provision this thing doesn't know these numbers. And the key insight is that the workload author probably does. So the person who's writing the Memcache model or the Cassandra model, they're extremely experienced in that workload. And they probably have metrics that tell them, like, I do 100,000 QPS and I spend this much time on CPU. So you can just like do some division and get these intervals. And we'll see that as we like dive in deeper, that these user desires are a composition of what the user is telling you and what the workload provider is kind of like giving by default. And we see that again when we get into data shape. So the user probably knows what the estimated state size is. Like they can tell you it's around 100 gigs or it's around a terabyte. But they probably don't know what kind of compression ratio your database is going to get on that data. Right? Like Cassandra uses a particular compression algorithm. It usually gets like a 2-to-1 to 3-to-1 compression ratio. And Memcache doesn't compress data at all. So this is important because if you don't take into account compression, you're going to over-provision by a factor of your compression ratio, which at scale is expensive. And it goes even deeper. Things like different workloads like JVMs are going to need certain amounts of memory for heap. And your system, maybe your kernel or your sidecars that run on this instance, they also need some reserved memory. And your capacity planner needs to know this information because it's relevant to like the minimum size instance that you could run that workload on. And you need to know that there's at least a minimum amount of memory. But trying to fill out these like very big JSON documents is probably hard. So at Netflix, we give people a nice little UI. They just click like, I want it in production, I want it in test. They say which regions they want it in. You'll notice that we don't actually ask them the service tier number because we found that was really confusing to people. So instead we just explain, like, would your service bring down Netflix? Does your service degrade Netflix? Just from those kind of English descriptions, people are able to select what tier it is. And then we give them these sliders, which you'll notice are order of magnitude estimates. So they're not giving us an interval. They're actually giving us a single point number where we're asking them, like, well, it's probably less than 100,000 and more than 1,000. And then we turn this into the user desire. So this is a user input that matches that UI input. So it's a service tier 1. It's a query pattern with expected value of reads per second of 10,000, writes per second 10,000, data size 100 gigabytes. And we're essentially assuming that the user is probably not off by more than a factor of 10. How many people think that users are actually off by factors of 10 all the time? A couple folks? Yeah, it actually does happen. But in general, it's a pretty good estimate that people probably won't be off by more than a factor of 10. We see about maybe 2 in 100, or 1 in 50, I guess. 1 in 50 people kind of being off by more than a factor of 10. So this is a pretty safe estimate. And we can then map those to those beta distributions. And this is kind of hard to read, so let's, there we go. All right, so we've got our reads per second, we've got our writes per second, we've got our state size. And then the model is actually going to bring compression, read size, how big are reads, how big are writes, how much time does it cost on CPU to read and to write. So we can see that like most of the inputs are actually coming from the model author. The user is actually giving you a relatively small number of inputs. And this is actually something that we found really important, because to make capacity planning decisions, you need to know a lot of this information, and the user doesn't know it. But luckily, the workload author does. And by giving people pluggable workloads like Elasticsearch, Cassandra, Zookeeper, et cetera, we can have the model authors who are experts in that model bring these inputs. All right, so now that we know exactly about computers, and we know exactly about how we think about user desires, how are we actually going to do some capacity planning? Right? That's why you guys came today, right? To actually do the capacity planning. So let's get some capacity planning done. Let's define this function. We now have the right inputs. We now need the right math. Don't worry, it's easy math. We're going to be multiplying some numbers. It's like the right numbers, but we're going to be multiplying them. And if that's scary, we already did the math for you. It's in the library. You can just call a function. All right, so let's dive in. Let's build a stateful model. A stateful model looks like this. This is the Cassandra capacity model, and it takes 5 concrete inputs. It takes a specific type of computer, so a particular instance type, a particular cloud drive, a regional context, like how many zones are there, the user desire, and then extra model arguments is kind of this backdoor where people just like put things for desires that we can't standardize. So an example would be like the Zookeeper model author wanted to know whether people were going to use it for locking use cases or leasing use cases. And that's relevant to one model. It's not relevant to all the models. So we don't lift it up to the capacity desires data structure. And the job of this function is to return an optional capacity plan. And you might ask, like, well, why is it optional? And the reason why is because if you ask me to run 1 million requests per second through T2 micros, there is no cluster of that will work. So these models are allowed to return like, nope, I cannot satisfy the user desire with that instance type. And a stateless model looks exactly the same. This is the beauty of the system. As you expand the workloads that are in the system, the like interface and the way that you implement them is more or less exactly the same. And the thing that just differs is how each workload calculates the inside of this method. All right, so in this talk, let's implement Cassandra. Let's go piece by piece. And the reason why is because Cassandra is the most complicated network, or the most complicated model at Netflix. Databases in general are the most complex software that you will have to capacity plan for. So let's see how to build the complex case. If we can do the complex case, then the simple case is easy, and we'll be OK. All right, so let's get into this. So how would we figure out how many CPUs we want? Well, we're going to use square root staffing. So we're going to take the average number of requests per second. We're going to multiply that by the average number of the average CPU time per request, and that's our value r. And then we add that to a quality of service parameter times the square root of r. And if you're curious, like, how do we figure out the quality of service parameter? The way that we do that is we define a probability of queuing. And we say that a tier 0 service, we want there to be a less than 1% chance that a request shows up at the server and doesn't have a free CPU to execute on. And that corresponds to a queue value of 2.375. And you can do the math for different kind of SLOs of queuing. And really, this is a proxy for latency. Right? Like we're really saying that tier 0s, we want to have very consistent low latency. And if you're curious of like, well, that's a pretty simple formula, right? Like, where did that come from? I highly recommend Performance Modeling and Design of Computer Systems by Moore Harcourt-Balter. It's an excellent book. Highly recommend it. And essentially, it makes some assumptions, which are probably wrong, but maybe useful. It assumes that you have an MMK system, which means that you have a Poisson arrival of events, you have an exponential distribution of response times, and you have k-servers. Reality, you probably have some kind of wonky arrival rate, and you probably have some kind of wonky service time, but that type of system has no math that tells you what to do. So we're going to use this, and if we're wrong, that's OK, we'll fix it. All right, so you have an MMK system. You bound the probability of queuing by setting a bound on the mean response time, and then you just solve for the value q under the normal assumption. And what that means is that you're assuming that a Poisson distribution and a normal distribution kind of look the same when you squint through them. All right, so if you're interested in like the math behind the math, this is the math behind the math. But I think it's reasonable to just say, OK, we're going to use square root staffing. We've figured out how many CPUs we need. And luckily, we have all those inputs. Right? Like going back to the user desire, we know how many reads per second there are, and we know how expensive they are. So we can just multiply those numbers together and get the number of CPUs. Next, when we're trying to do network, at least at Netflix, we find that you can use a pretty simple network model. So you take how big your reads are, how big your writes are, you multiply them by their rates, and you add some kind of like fudge factor. The fudge factor in practice is usually like 2 or 3. You're essentially saying, leave this much extra headroom on my network for backup, for repair activities, for things that my model doesn't encompass. In practice, this works pretty well for most data stores. The one exemption to this is our memcache model, which actually cares very deeply because memcache can absolutely saturate EC2 NICs. And for that one, we might have to take into account things like when I do a write operation, how many copies of that write am I doing? So I have 1 byte in, I have 9 bytes out. So this can get tricky in the complex case because we have to know like how many replicas do I have to consider, how many things do I have to talk to for a read or for a write. But again, spend your complexity where it makes sense. For most models, this is not the place that it makes sense for you to spend any time thinking that much about, except for memcache. And again, luckily, we know all these inputs. We know the reads per second, the read size, the writes per second, the write size. We can just multiply those numbers together and get our network. All right, so now we're on to the parts that start getting tricky. And luckily, the next two really only apply to stateful services. So if you're running stateless services, you can kind of ignore this. But disk is very model specific because every single data store kind of lays out data on disk in a different way. So for example, Cassandra uses a particular compaction strategy. Elasticsearch uses a different merge strategy. And depending on like how LSM trees lay out data, you're going to have a different amount of wasted disk space on top of the user. So like if the user is storing 100 gigs, Cassandra might take like 130 or 140 gigs to actually store that. And this has to do with every single storage engine and how they lay out data. So you take how many copies of data you have, you multiply it by the input size, you divide by how many zones you're splitting it over, and then you multiply by your compression ratio. This gives you how much disk space you have per zone. And then you can estimate based on the previous 2 numbers how many nodes you have, and then multiply it by this like function compaction. Whenever you see me say like F compaction or something, that's me essentially saying like there's a bunch of math here. Let's just pretend that it does like for the sake of this talk, it's some function of your data store's compaction strategy. And then that's how much space you need per node, unless you're using network drives. If you're using network drives like EBS GP2, then you have to take a maximum of that size and buying enough space to get the I/O that you need, which is a function of read bandwidth or write bandwidth. All right, so now we know how much disk space to use. And now we get to the point where we're starting to involve almost every parameter that the user has given us, right? Because we need to know how much state there is. We need to know how much the compression ratio. We need to know the rates in order to get the bandwidths. We need to know the size in order to get the bandwidths. And now we get to the real fun stuff. So this is my slide of memory is hard. So everything's just a bunch of functions. If you're curious what these actually mean, just go to the code and you can read like how we determine this for Cassandra or memcache. And the reason that memory is hard is because there's a fundamental trade-off between where you spend your memory. You can either spend it to make reads faster via caching, or you can spend it to make writes faster via buffering. Almost every stateful service uses some form of this. In MySQL, you've got the buffer cache, and in Postgres, you've got the page cache. In Cassandra, you've got your on-heap mem table. And so the amount of RAM that you need for read is dependent on how big your data size is and your working set. So for example, if you have 100 gigs and you have a 10% working set, you need 10 gigs of RAM to cache the reads on that node. The amount of memory that you need for writes is dependent on your write bandwidth and that compaction strategy. Depending on how the data store is relaying out data, that impacts how much extra kind of memory you need to flush less often. And then there's like the properties of the software itself. So for example, if you have a JVM data store, you have to allocate enough memory for your write bandwidth and your read bandwidth to flow through the JVM. And if you're running a bunch of sidecars in your system, then you need to allocate enough memory for that too. So the amount of memory that we need per node is kind of dependent on every one of these components. And then you calculate that per workload, you add them up, and that's how much memory you need. And this is a little bit tricky because this does depend on the number of nodes. For example, if you tried to fit a Cassandra database on one giant node, it wouldn't work very well because due to compressed oops, you can't really make your heap larger than 31 gigs. So each workload is going to have different kind of like odd memory layout issues that might bias you towards, for example, doing more smaller instances. But luckily, these can be encapsulated within the complexity of the model. And again, we're involving almost every input that we have. The only inputs that we're not considering for this are the on-CPU time, because those don't matter for RAM. All right, so you notice that I snuck a hard one in there, which is the working set. I just breezed right by it. People know how much of their data they read. Who here thinks that people know how much of their data they read? Nobody, right? Nobody knows how much data they're going to read. So we kind of had this problem because we don't know how to buy RAM if we don't know what's the hot set. And the way that we solved it at Netflix was we kind of inverted the question. Instead of asking what's the hot set, we asked, given the latency of the drives we have, and given the latency SLO that we have, the promise that we're making the user about how fast reads are, how much memory do we have to buy? So for example, here is a distribution of an NVMe flash drive. This is ridiculously fast. 120 microsecond typical read latencies. Ridiculously fast. You don't need memory in front of this drive, or at least not very much. Contrast that with an EBS GP2, which is 10 times slower. Your typical read latencies will be 1 millisecond. Slower disks need more RAM in front of them to cache reads. So this leads us to a realization. We can calculate the working set, which is essentially, in this case, just how much RAM do I have to buy, from the promises we make. And you can think of that like you take your latency service level objective, and you compare it to the drive latency distribution. And you ask, how much memory do I have to buy to guarantee that my service meets my SLA, or my SLO, given drives which do not meet my SLO? So for example, if EBS GP2 has a P95 latency of 1.35 milliseconds, then a database that has a 5 millisecond P99 latency SLO, then we only need about 45% of our data in RAM to guarantee that we will meet that SLO. Contrast that with a cache, like Memcache, which has, at Netflix, our caches carry latency SLOs of less than 1 millisecond. We need 100% of our data in RAM. We cannot rely on GP2 at all for a cached workload. And this insight really kind of allowed us to move forward because it allowed us to figure out how much RAM to buy to cache reads. So great success. We figured out CPU, network, disk, RAM. We can capacity plan for a specific instance type and a concrete user desire. Oh, we have a problem though. We have dozens of shapes. We have lots of cloud drives to consider. We need to solve a more complex problem than one instance and one user desire. Solution? Trusty for loop. We can just kind of loop over all the different inputs, all the different possible instances, filtering out the life cycles that we should never deploy. We feed them through the model, and for each different kind of concrete instance type, we get out like, well, if you force me to buy M52s, I need 12 of them. If I buy R5D2s, I need 6 of them. And then you just pick the cheapest one. And you can intuitively think of this like, OK, I figured out how much CPU, RAM, network, disk I need. And this is just saying, how can I most cheaply buy the resources that I need with my current pricing? Great success. We can capacity plan over all instances and cloud drive types with a concrete user desire. Who sees what's coming next? We don't have a concrete user desire. We have like 20 distributions that could lead us to millions of possibilities. So what are we to do? Any guesses? We're going to capacity plan with uncertainty. And the way we're going to do that is with Monte Carlo. It's a ton of fun. All right, so Monte Carlo, we simulate possible worlds. We have these generative distributions, so we can do this. We can simulate the possible worlds. And we're not trying to get the world that actually will exist. We're just trying to get enough simulations that we will encounter tail events. The time where the user was off by a factor of 10. The time where they actually needed 4 times more disk space than they thought. And we're going to pick the cluster over all those worlds that is the least regretful over all worlds. Sounds kind of fun, right? Least regretful cluster. Yeah, we're going to provision the least regretful cluster. But how do we define regret? Well, at Netflix, we regret money. We regret buying too little computers. That's called under-provisioning. We should have bought 100 computers. We bought 10. Oh, man, we're under-provisioned. We also regret buying too many computers. That's wasting money, right? We could have used that money to make more episodes of Friends. We don't want to spend that on computers. We also regret operator time, because operator time is also money. If I have to recover a cluster that is run out of disk space at 2 in the morning, that is expensive to my company. So I want to bias towards not having to spend operator time either. Operational overhead, over-provisioning, under-provisioning, they're all just different forms of money. And how much your organization cares about these different kinds of costs is dependent on your organization. For example, a startup probably cares more about over-provisioning than under-provisioning because they don't have a lot of money. A company like Amazon probably cares about over-provisioning and, under-provisioning and having an outage. Don't want to have a shopping outage. Don't want to have Netflix go down. So the parameterization of regret function is tunable by the user of this library. Just like you can bring your own pricing and your own lifecycle, you can also bring your parameters of regret. How much do you care about over-provisioning? How much do you care about outages? And then the least regret is just the world, which when compared to all the other worlds, is the least regretful per this function. All right, so let's dive in and actually do some examples. So the regret function is pretty simple. It takes parameters. Those are those constants or exponential values. It takes a plan that we bought, so a set of computers that we bought, and then a proposed plan. The proposed plan is the one that we bought, and then optimal is the one that we should have bought. And then the cost model is how much do we regret this choice? We should have bought this computer, and we actually bought this computer. How much do we regret that? So let's work an example. Let's say that in world 1, the particular set of inputs in world 1 leads to us buying 48 i3 NX large computers costing $73,000 with 6.6 terabytes of space. In world 2, we have a bunch of crazy tail events, and we end up buying a really expensive cluster. 96 R5 8X larges, $500,000, 18 terabytes of disk space. And we can just calculate the regret. So let's first think of us buying the world 1 computers, but we live in world 2. So we bought 48 i3 NX larges, but we needed to buy 96 R5 8s. We have 6 terabytes of disk space, and we needed 18. And so we can just plug those into our regret formula and come up with, well, we regret this to a tune of about $10 million of regret. And we're under-provisioned. We can also do the math the other way. We can say, OK, well, we needed to buy, we bought world 2 and we lived in world 1. So we needed to buy 48 i3 NX larges, and we bought 96 R5 8X larges, and so on and so forth. You can do the math here again, and you can say, OK, well, if we buy world 2 and we live in world 1, we have about $8 million of regret, mostly coming from us not having any disk regret, because having too much disk is not a problem. Having too little disk is having a problem. And this brings us to a realization, which is that regret is not symmetric. Choices of constants determine the relative cost for your organization of under-provisioning and over-provisioning. In this case, because of our parameters, the under-provisioned case was less regretful than, the over-provisioned case was less regretful than the over-provisioned case. However, that tail event cluster is probably the most regretful choice when you compare it to every other option. So even in that particular local example, it was less regretful. When you add that up over 1,000 simulations, it's almost never the right choice. It's almost never right to spend that much money. So let's work an example. Let's use that example from earlier before, 10,000 reads, 10,000 writes, 100 gigs of state. So to get the least regret cluster, we're going to feed it into the capacity planner. And here you can see us registering the Netflix models. If you were doing this for your organization, you'd register your own models. Maybe you have different decisions than we do, different workloads. And then you ask the capacity planner to plan with the Cassandra model. We're going to run 1,024 simulations. We'd like to get an explanation of the result. We see something like this. The least regret choice for this is 12 M5D X larges costing roughly $9,000. And the interesting thing about this use case is that because the state size is so small, we're essentially always buying M class. There's almost never a reason to go outside of M class because you're just buying disk you don't need. And we can kind of, if you look at the right-hand numbers there of how many times we bought that particular cluster, you can kind of see the input beta distribution reflected in the output. And that's really kind of the key to this, is that we're going through this crazy nonlinear function, but at the end of the day, we're still able to pick one of these clusters to actually go buy. Now let's make the problem harder. Let's make the interval really big. In this case, we're going to consider 100,000 to 1,000,000 writes per second, storing between 10 and 100 terabytes of state. Now, when we do the same thing, we take that input, we feed it through the capacity planner, we run 1,024 simulations, we get a lot more options, right? Because depending on where we end up in that input space, it might make sense to buy i3ENs. It might make sense to buy our M5Ds. It might make sense to buy R5s. But the least regretful choice is still a pretty reasonable 48 i3 ENX larges costing roughly $73,000. There's a lot more variability in this one because the user input was less specific. 100,000 to 1,000,000 writes per second is a big user interval. There's a lot of uncertainty here. But even with all this uncertainty, we still pick that exact cluster a large number of the times. And the regret of a cluster to itself is 0. So those zeros usually cancel out most of the things. So let's try to get some intuition about what just happened when we ran that least regret optimizer. Intuitively, what happened was we biased towards choices which are a little bit down that tail. So in this case, the red line is in this world, so this is the world where we picked the 48 i3 ENX largest, the least regretful choice. In that world, we had slightly more writes per second and data size, and our reads were a little bit more expensive. And if you look at that tail cluster, the really expensive one that we would never buy because it's super regretful in general, that cluster had 3 major tail events. It had a lot of size, it had a lot of writes, and whenever you would read from it, they were very expensive read queries. So again, I just want to emphasize that we're not trying to provision for this. We're just trying to bias our choice a little bit down that curve and just move it away from the average just a little bit to kind of hedge our bets. Because the user input was super vague, right? Like, they gave us an order of magnitude input. We could be off by a lot. So this is excellent, because now we've succeeded at capacity planning with uncertainty. We've gone from a super uncertain user input, a description of our hardware, to a concrete, go buy these computers. They're the least regretful choice, which I'm going to call optimal. But you could also just call it least regretful. But again, going back to the beginning of this slide, this is just a model. And models can be wrong. And especially when we're dealing with uncertain user inputs, we have to be able to monitor that we've made the right choices after the production launch. So after they actually launch the load and we find out where they actually are in that distribution, we can monitor. So how are we going to monitor if we got enough CPU? The way we do it at Netflix is we measure CPU worker queuing. This is pretty different. Most places that I know monitor CPU utilization, and we think that's wrong because utilization isn't actually telling you whether buying more CPUs would help you. Who remembers the meltdown issues a couple years back, where like all of your CPUs, only one person remembers meltdown? Okay, all right. Yeah, meltdown was a pretty big deal. And all of your CPUs got slower as the mitigations went in. So we had a bunch of people clamoring like, oh, our databases got slower, we need to scale up. And what we did was we gathered this metric and we showed them graphs that had 0 CPU queuing. We were like, sorry, your database is slower. Buying more CPUs will not help because we're never queuing, waiting for a CPU. The moment that something shows up at our database, it's executing. And luckily, Linux gives you this number that you can collect in like 8 lines of Python. This is not that hard to measure, not that hard to understand. And just as an example, this is that metric plotted for 2 of our clusters. The tier 0 is a very latency sensitive important cluster. Remember that we paid extra money to have what percentage queuing on this cluster? Less than 1%. Have we met our goal? No queuing. It's fantastic. That's correct. The tier 3, how much queuing do we have on that? We have roughly 30% queuing. That's also matching our model. We wanted to have about 30% queuing on a tier 3. So we look at these graphs and we go, yeah, like this looks all right. We don't need to buy more CPUs for the tier 3. It's a tier 3. We're OK on the tier 0. However, if you saw that tier 3 graph on a tier 0, you're in trouble. You need to scale up, get more CPUs. All right, so we know if we need more CPUs. What about disk and network? We just use utilization for disk and network. Disk space is pretty straightforward. If you actually are using 60% disk space and you wanted to be using 30% disk space, you need double the disk. And just to like really emphasize this, you're probably going to be wrong on disk space because there's a very important part of that model, which is the compression ratio, and it's really hard to predict that. Right, like we're kind of predicting roughly like 2 to 3 for Cassandra, or roughly like 5 to 6 for some of our columnar stores. But the reality is that you don't know that until actual data starts hitting your data store. But the good news is that it's easy to know if you're wrong. You just measure how much disk space you're using, and if you don't have enough, you scale up. That's kind of the wonderful thing about EC2, is that when you make a mistake, it's not that hard to recover from it. On network, it's the same thing. You can watch your network bandwidth, your utilization, how much of that baseline network am I using. And here we can see like an interesting work pattern. Like that's a backup running every hour, right? And using a bunch of network bandwidth. That's why burst is really useful. But we still capacity plan for the bottom number, not for the top number. All right, how about memory? Memory, as with all things, is the most complicated one. We actually find it very difficult to measure if we have enough memory. And instead, we measure kind of proxy statistics. So for example, when we're trying to figure out if we have enough memory for read, we don't measure the memory, really. We measure how many disk reads are we doing. Because if we're missing the page cache, or if we're missing the block cache, and we're doing lots of disk IOs, then that means that we probably don't have enough memory to cache reads. This number, whatever this reads per second or writes per second should be, should be significantly less than your drive's read I/O capacity. Which, if you remember back from that slide about the computers, we know how many read IOs every computer in EC2 can do. So we can know if we have enough memory for reads. And if you want to get really fancy, you can use tools like BCC's cache stat, which will actually give you a percentage of like what percentage of the time is the kernel going to do a read and is missing the cache or hitting the cache. At Netflix, we don't actually get that fancy. We just use the proxy metric. Writes are also a little bit complicated because really, like, you can see writes to disk, but the problem with that is that most stateful services will kind of like group up together writes and like flush them all at once. So you'll see a graph that looks like I'm doing no write IOs, then I'm doing all the write IOs, then I'm doing no write IOs, and I'm doing all the write IOs. So instead, we usually monitor proxy metrics such as how frequently is your stateful service doing a flush operation. And we usually target like less than roughly one per 10 minutes. And that's kind of like hand wavy, and I know it's hand wavy, but that's what we do. We monitor the flush frequency, and if it's too high or too low, then we either adjust the amount of buffer space we have for writes, or we give it more memory. All right, so by looking at these metrics, we've maybe decided like, hey, I ran out of network, or I ran out of CPU, or I ran out of disk, or I ran out of everything. And one of the wonderful things, again, about EC2 is that they probably have a computer that optimizes for exactly what you ran out of. So if you're on the M5 class and you ran a network, then you can just kind of switch over to the M5N class, which has more network, same ratios of CPU. If you ran out of CPU, you can move over to a CPU-optimized instance family. Or if you run a disk, you can move to a storage-optimized instance family. And if you run out of everything, well, you just got to scale up. Either go out wide or go up vertically. It's pretty simple. Monitor what you ran out of, buy more of what you need. The wonder of the cloud. All right, so in conclusions, today we have understood our hardware, we measured, priced, and imposed lifecycle on our hardware, and then we were able to apply queuing theory on those concrete inputs, simulate worlds, pick the least regretful world, and then realize that even with all of this complex modeling, we're still going to get it wrong some of the time. And when we get it wrong, we just have to monitor our choices and buy more of what we need. And again, I just want to say the system is open source. It's pluggable. You can layer your own information. It's on our Skunkworks GitHub. I really hope that some folks check it out. And with that, I just want to say thank you. Thank you all.